Alright, this is lesson 10.4 and we're going to do two topics today. One more topic on polar stuff. We're going to talk about polar arc length, and then we're going to look at the last part of the unit which talks about vectors and vector calculus. But before we do that, I need to give you some vector definitions. So the last topic in the polar realm is this thing about arc length. You see this formula here, and it does look very similar to the other arc length formula that you hopefully would have remembered. Remember the parametric one? Integration of a to b, square root of dx dt all squared. Oops, ran out of batteries. And then dy dt all squared dt. Yeah. So we can actually use this idea of replacing the theta with, replace the t, I should say, with theta. And then also using these ideas of x being equal to r cos theta and y being equal to r sine theta to actually produce this formula here for the polar arc length. Okay, I won't show that to you here in this video. If you do want to find out, you can find out and let me know, and I can do it for you in another video if you want, or in class. So really then, for this example, straightforward, you just need to know how to apply the formula. So find the length of the arc from theta equals 0 to 2 pi for this lovely curve. And the formula here says, yes, you do need the integral from a to b, so in this case 0 to 2 pi. And then it's the square root of, and yes, it's r squared, so 2 minus 2 cos theta, all squared, plus the derivative. Okay, so what is the derivative of r? I guess I could do that up here. dr d theta, the derivative of 2 is 0, the derivative of cos is just negative sine. So multiplying that together, yes, just 2 sine theta. And then don't forget d theta, and yes, this is the formula that allows you to calculate the arc length. Now once again, we're not going to do this by algebra, this is way too complicated, so all I'd like you to do now is just punch this into your calculator and get the actual answer. Okay? And I won't do that for you, I'll just give you the answer right now. I believe it's 16.000. Okay? So just a simple application of a formula. And once again, if you really want to know how, then you can try this as an exercise. All this stuff here. Let x equals this, let y equals this. I'll tell you the next step is to actually find dx d theta. Don't forget using product rule. dy d theta using product rule, and then you can stick it into here. Okay? Because once again, all these things are theta. All right. So now let's talk about vectors. Okay, we have some definitions that I need to describe to you. What is a vector? Well, a vector is really just a directed line segment, meaning that the direction matters. Okay? And so here is an example of a vector. It's going, I don't know, in the north-east direction, I guess. We can talk about something called the magnitude. Okay? And the magnitude of the vector is really the distance, and we use these double bars. So if I were given an x value here, and also a y value there, the magnitude or the length of the vector, well, that's just, yes, using Pythagoras. X squared plus y squared, and then take the square root. Okay? So that slanted distance, or the magnitude of the vector, is the square root of x squared plus y squared. Okay? To describe the direction, we're going to use an angle. I'm going to use this angle called theta. So this angle here is found by taking the inverse tangent or arctangent of the ratio of the y over the x value. Okay? That's how we describe the direction using an angle, and this would be an angle in standard position. Okay? You might be thinking, what's an equivalent vector? Well, an equivalent vector is just one with the same magnitude, so the length is the same. But also, it has to go in the same direction. Whoa, what happened there? Undo. Oh, whoa. Where did they go? Next. Yikes, 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 yikes. There we go. Same magnitude, same direction. Okay. Now, you need to be aware, we don't want the same starting and ending point though, because then it's just really the same vector. So just a note, not the same starting or ending points. Okay, and then the component form of these things, well, that's just, yes, we use an x component and a y component to describe it. And we use these like, I don't know, less than equal signs, kind of like, I won't call it a square bracket, but just more pointy, pointy brackets, I guess. Okay, so with that in mind, let's go through examples number 2, 3, and 4, and this will hopefully give you a good understanding of what a vector is before you do some vector calculus in the next video. So I've got an initial point of a vector. It's negative 1 comma 3. I'm just going to plot that right now. Negative 1, 3. And then its terminal point is 2, 7. So 2, 7. And I'm going to connect them together and actually draw the arrow so we know the direction. It's going this way. Okay, starting to the end. So I've graphed its vector. Okay, I've done that. And then it says graph the vector in standard position. So when I do part B, graphing in standard position, what I mean now is I want you to translate that vector and make it start at 0, 0. And we know that if you think about it, the components here, it looks like it goes 1, 2, 3 to the right, and then 1, 2, 3, 4 up. So I want to do the same thing here now, 3 to the right, 4 up. And then here is the vector for B. Okay. Oh, I just did part C for you. Give the component form of the vector. We just told you we went 3 to the right, so that's the x value, 4 up. So here is our component vector. And then if you want to find the magnitude, which is the length, yes, you just take the x value and square it. Add to that the y value and square it. And then don't forget to take a square root, so that's just 5. Okay? And ultimately, the direction of the vector, once again, is the angle theta. And both of these have the same angle, because I just shifted it down. You'll find that this is just the inverse tangent or arctangent of the ratio of 4 over 3. And you can use your calculator to calculate this. I think I got an answer of 0.927. And yes, this is radians. Okay. All right, so there you go. Basic parts. I hope that's okay. Number 3 says find the direction of a vector given by these components, negative 3, comma 5. Now, once again, it really doesn't matter where you start if you want to draw this out, but naturally, I think the easiest part would be to start at the origin. So if I did that, my components are 3 to the left, 1, 2, 3, and then 5 up. 1, 2, 3, 4, 5. Ooh, like this. Okay. And so I'm asking you for this directional theta. And yes, that theta is still going to be the arctangent of, in this case, of 5 over negative 3. And if you think about this, and you do this in the calculator, I will actually do that with you this time. Turn it on, calculator, go to here, arctangent 5 divided by negative 3. Where's my negative button? Oh yeah, negative 3. Ah, I got negative 1.030. Now, if you left your answer like this, ooh, your pre-calculus teacher will be sad. Because this angle is a negative one, which means it starts at the positive x-axis and goes clockwise. But that's not the angle I want. So how do we figure this out? Actually, negative 1.30 is actually this angle here. That's theta, negative 1.030. But the one I'm looking for is in quadrant 2. So if you're thinking, do I have to add something to it? Yes, you do. Your angle theta is actually not negative 1.030, but it's that plus pi. And I think that's just 2.111. Okay? And that will be the correct answer for this in quadrant 2. And finally, now example number 4, if the magnitude of the vector v is this, then its direction is theta equals to 2/3 pi, then can you write the vector in component form? I hope you certainly can. Because if you're thinking about what's going on here, I can draw an angle, probably something like this. This angle here is 2 pi over 3. And if I actually want the components, I'm asking you to find the y component here and also the x component here. That you can see that if the length or the magnitude is 6, then the x value is just going to be about 6 times cosine of 2 pi over 3, right? Comparing trig in x, right, over r is the cosine angle. And then similarly, the y component will be that 6 multiplied by the sine of 2 pi over 3. Okay? And then 2 pi over 3 is special angle. You should know what that is. Cosine 2 pi over 3, I believe, is negative half. So this just becomes negative 3. And then sine 2 pi over 3 is positive, I think it's root 3 over 2. So 6 times root 3 over 2, that's just 3 root 3. So in this case, if I ask you for the vector in component form, we'll see that it's actually negative 3 for the x component, and 3 root 3 for the y component. C'est fini. We're done.